Hi everyone, my name is Noman Bashir and I am here to present our paper on probabilistic approach to solar energy commitment in the day-ahead electricity market. Solar power continues to grow at an exceptional rate over the years. This is primarily driven by reducing costs of solar, which have dropped approximately 10% per year over the last few years. This large-scale penetration has increased the amount of solar in the grid. Instead of a grid where power flows from large generators to household, we now have flow in the opposite direction as well. Also, the variability in solar increases the stochasticity of demand. These two things combined make balancing supply and demand very hard for the grid operators. States in US and countries across the globe are responding to this challenge very differently. One response used by many places is to impose limit on the total installed solar capacity. Once the limit is hit, no further installations are allowed. Some countries with low penetration allow unrestricted injection of solar power to the grid. However, this is not a long-term sustainable solution. One of the better approaches is to ask solar sites to participate in the electricity market, just like normal generators. This solution has challenges of its own, and our work focuses on addressing one of those challenges. I would like to provide a brief overview of electricity market. Electricity markets generally have two sub-markets. The first one is day-ahead market, where generators commit power for each hour of the next day based on the forecasted demand. As forecasts are not perfect, any difference between the actual demand and scheduled generation is handled in real-time market. We only focus on the day-ahead electricity market as it handles most of the energy transactions. Also, the real-time market requires short-term solar power forecasts. While our approach is applicable to short horizons, there are better approaches available for short-term solar forecasting. Therefore, the participation in real-time market is out of scope for this paper. Unlike traditional generators, solar sites, however, do not know how much can they produce tomorrow, as it is a function of weather. This uncertainty results in a loss of revenue. If you underpredict and produce more energy on the next day, you either curtail power or use expensive storage to store the excess energy. If you overpredict, you cannot fulfill your commitment and incur a penalty. There is a need for day-ahead energy commitment approach that tackles this uncertainty in power forecasts, and we need while making a commitment in the day-ahead market. We next look at those factors on which the solar power forecast for solar power depends and how the forecasts are generally made. Solar power for a solar site depends upon three things: location, weather, and physical parameters of the site. Location determines how much irradiance comes from the sun. Weather determines how much of it reaches to the ground. And finally, physical parameters of the site, such as capacity, tilt, and orientation, determine how much irradiance is converted to power. A solar performance model takes all of these variables into account while modeling a solar site. Modeling the effect of cloud cover is the most challenging task. And Solar Decay is a solar performance modeling and forecasting toolkit released by our lab. This explicitly models the effect of cloud cover. As we discussed on next slide, modeling the effect of cloud cover is the key part of our approach. We use Solar Decay as its extensible and modular design allowed us to integrate the probabilistic approach easily into an existing framework and perform evaluations. Before I go into the details of our work, I would like to mention some other approaches to solar forecasting and discuss their shortcomings. There is a lot of work that feeds a solar site's historical generation and weather data to a black box ML model and predict the power output. This approach, however, requires a lot of data for training and cannot be used for new sites which have little to no data. There is also work on estimating ground level irradiance and then converting it into the power. This work generally requires ground level irradiance sensors, which may not be available on all residential sites. Finally, there is work that uses the state-of-art cloud cover forecast, models their impact on output, solar output in a deterministic manner, and predicts the solar power output. We use this work as a baseline in our evaluation. With enough background, we can dive into the key insights and our solution. The key insight of our solution is that the error in solar power forecast can be decoupled into two components, and these two components can be modeled separately. The first source of error are the inaccurate cloud cover forecasts. We all are aware of this problem. Sometimes weather gets cloudy and rainy without the appropriate forecast, and at other times it is quite hot and sunny while we were expecting rain based on the forecast. The other source of error is a bit hard to grasp, so please pay attention. Our analysis of thousands of solar sites show that even when we know the percentage of clouds in the sky, we cannot precisely tell how much irradiance will reach the ground. On a day with scattered cloud, we all have seen patches of land with full sunshine and the other spots with complete dark clouds. Solar panels are basically irradiance sensors, and they may experience and measure the cloud cover effect differently based on their local view of the sun. This leads to measurement error. Given this insight, our solution is to use historical data and build error distribution for both forecast and measurement errors. We then use these models to quantify uncertainty in solar power and devise a commitment strategy that honors this uncertainty. Later slides will show that this approach is applicable to all sites, new or old. Before I go into the details of our implementation, I would like to discuss the source of weather measurements and forecasts used in our approach. The forecasted cloud cover and temperature data comes from numerical weather prediction models run by National Weather Service in the US. While these models are state of the art, they are not perfect. The inherent deficiency in modeling approaches and the initial conditions used for simulation limit the accuracy of these models. Also, NWFP forecast cloud cover as a percentage, while the observed data sources generally report cloud cover as one of the five values. So these five values basically describe how much of the sky is covered by clouds. For example, a few cloud cover string represents that approximately 12.5 to 37.5% of the sky is covered with clouds. The definitions of five levels are given in this table, and like they can be viewed for detail. Using the data that we just discussed, we compare the forecast and cloud cover. We compare the forecasted cloud cover with the observed weather data. This figure has forecasted cloud cover on x-axis and probability of observed cloud cover on y-axis. We can see that, so for example, for a clear forecast, the it tells the probability of the actual observed weather being one of like each of these strings. We can see that the cloud forecasts are highly inaccurate, and this distribution is just for 3 p.m. when the forecast was made at 8 a.m. on the previous day. We generate such distributions for each hour of the day. One key observation from this analysis was that uh, the extreme cloud cover forecasts are generally more predictable. If you look at the overcast forecast and clear forecast, they have the highest accuracy in terms of the actual weather being the same as forecast. We next analyze the observed weather data for example sites in states that differ in general climate. This figure has different states on x-axis and the availability and the probability of each cloud cover on y-axis across all times. The site in Texas, for example, observes extreme weather of clear skies most often. And since we have established that extreme cloud covers are easiest to predict, cloud cover forecasts in Texas are generally more accurate. And because weather is more predictable on some sites than others, this means that the forecast error distribution needs to be computed for each site individually. So far, we have discussed the forecast error. We next discuss the measurement error distribution and show why it is universal. If we look at just the raw power of the solar, it varies over time for a site as the irradiance level changes across the day and the year. And across sites, the capacity of each site and installation characteristics makes the power different for each site. However, these differences can be easily removed by normalizing the actual output of a site with maximum power it can produce under clear skies. The ratio between the two values is termed as the normalized clear sky PV index or KPV. The following figure have time on x-axis and power on left y-axis and KPV on right y-axis. We see that even though power values are different throughout the day, KPV values at different times can be the same. For example, KPV at 12 and around 17 hours, it is the same. So this normalization basically means that the KPV values over time and across sites are directly comparable. And to quantify measurement error, we use KPV instead of raw power generation of a site, which makes our model universal. We next discuss the measurement error in KPV. The figure on the This figure has a cloud cover on x-axis and KPV values, observed KPV values on y-axis. We see that for a given cloud cover, the observed KPV can be widely different. The curve fitting gives us an equation that provides expected KPV for a given cloud cover percentage. There are two issues with this approach. First, it is a deterministic equation that gives a single value as the output and does not leverage the full information available from this distribution. Second, it takes cloud cover as a percentage while our data is measured in 5 different levels that I have discussed before. To handle this problem, we map the figure on this left to this figure on the right, which gives the probability distribution of KPV given a certain weather. Our empirical analysis has resulted in two error distributions. In the error distribution, we get the probability of each cloud cover given a cloud cover forecast. In the measurement error distribution, we get the probability of KPV given a cloud cover observation. We combine the two to get a conditional distribution that gives the probability of each KPV value given a cloud cover forecast. In this figure, we have an example CDF for one particular hour with one particular forecast. Given the forecast of broken sky, it tells us the probability of being lower than any KPV value. These distributions are uh, generated individually for each forecast and each time of the day. We use these to decide on how much power should a solar site commit. After building these distributions, the next part was to devise the energy commitment strategy. The goal is to maximize the expected revenue given the day-ahead energy price and penalty to pay for overcommitment. We assume that we know both price and penalty. In practice, they need to be predicted. These prices are highly predictable, however, as they are a function of demand on the grid, which is easy to predict because the demand on the grid is largely a function of temperature, which determines the heating and cooling load. The overall expected revenue can be computed using law of total expectations. From the distribution that I showed on the last slide, we have the probability of under and over commit. The overall revenue can be computed, the expected revenue can be computed is as expected revenue when you undercommit into probability of undercommit plus expected revenue when you overcommit into probability of overcommit. And in the undercommitment case, our revenue is basically because we we can fulfill whatever commitment we made, we get the price for our energy commitment. In overcommitment case, because we cannot fulfill our energy commitment and actual energy is less than the commitment, so we get the price for the actual energy that we provide, and we also pay a penalty for any deficit proportional to the deficit. All of these values are a function of KPV. If we increase the KPV that we commit, for example, if I commit 0%, there is no revenue, there is no loss. But if I commit 100%, I will get some revenue, but also expect to pay penalty because site may not produce maximum. So as we change the commitment level KPV, we compute expected revenue at each KPV, and we pick the commitment level that gives us the maximum expected revenue. Because we have only finite levels of commitment, 0 to 100%, we use a brute force search, and we do not need any complex optimization procedure. We evaluate our approach using a solar site in Massachusetts. It's a residential site of size 10 kilowatt, and we take the price data from ISO New England for that location. We evaluate the approach using multiple metrics. The first one is the amount of revenue generated by the site, and higher value is obviously better. The next one is overcommitment. This is important because if sites overcommit and cannot fulfill their commitment, grid has to balance the deficit using expensive backup diesel generators, which reduces the reliability of the grid and increases the costs. So an ideal strategy would not overcommit at all. We compare the revenue generated by our approach with two baseline approaches. The first one is the state-of-the-art approach that trusts the weather forecast from numerical weather prediction models. And then it uses the empirically generated conversion model that for a given cloud cover, it gives the expected power. The other strategy is the maximum commits the maximum expected power for the next day without considering the cloud cover. To compare revenue across different approaches, we take price data and set penalty as some percentage of day ahead energy price. We see that our approach performs better than the deterministic approaches, especially at high penalty. We next evaluate overcommit levels for different strategies. We have discussed that our overcommitment affects the grid operation as it has to make up for the deficit. Interestingly, undercommit for a solar site is desired for the grid, since the site curtails power in this case and provides a stable power output. In this graph, we have penalty on x-axis and energy commitment on y-axis. It shows that while baseline approaches always overcommit, the probabilistic approach undercommits at high penalties. It is interesting to note that while our site generates more revenue, it still undercommits. So this is safer for the grid. All of the previous results do not consider the energy storage. We purposefully excluded energy storage from the problem of finding the right commitment level. We did that to isolate the effect of probabilistic forecast from the effect of battery. However, we perform an analysis where the site uses battery to store energy when it undercommits and uses the stored energy to make up for the deficit when it has overcommitted. The following figure have battery capacity on x-axis and revenue on y-axis. As the battery capacity increases, the revenue increases. However, after some value of the battery capacity, the battery cost becomes more than the benefits gained by the battery. To conclude the talk, we discussed the error in solar power forecast and decoupled the error to different components. We then devised a probabilistic forecasting and energy commitment approach. Using the data from a solar site, we show that our approach yields more revenue and is safer for the grid. Thank you, and I can take questions.